We're going to talk now about hybridization and how this model allows us to explain something we call electron delocalization. So let's start with a molecule, and I'm going to just draw the line, right? We learned about line drawing. And so this is a little carbon cation. And now, in like that, you will see that the charge is kind of in one carbon. But actually, let's draw the molecular orbitals to understand how electron delocalization can happen. And so I'm going to start doing, here is my backbone. And I'm going to say now, what is the hybridization model? So here I have an sp2 carbon, another sp2 carbon, and here we're going to say this is also sp2, but we're going to have one empty p orbital. So let's do the drawing now. If these are in a plane, well, I'm going to draw for the, hold on, I need to erase this to make a nicer picture. I'm going to just draw the p orbital. So I'm going to say that if this is our backbone, I'm going to have one p orbital here, another p orbital here, and one here, but this one is empty. This is a carbon cation. But as you see, we could have an overlap here in, say, a pi bond, and that will be the representation of what we have here. Or I could say that this overlap. And so, and in fact, what happened is that we have, this is a picture using just atomic orbitals, p orbitals. I'm just drawing the pi system here, say. So where are the orbitals? And I'll take it into account at this point, where are these sigma electrons? But now I could have thought in a pi bond to the right-hand side, let's say, and another here. But actually, you cannot distinguish. In the real molecule, what's happened is that we make a molecular orbital, and this time I'm going to make another drawing. What happens is, like the electron density is like all over here. So we have that overlap. Let's say that this is my electron density. I'm going to use one color here because we always say that p orbitals have, say, one lobe, and we color one color simply because these are mathematical functions and we assign them different signs. So this will say that this is a picture of the molecular orbital and say bonding molecular orbital. What that means is my electrons are going to be spread into the three atoms. So, and also the positive charge. So in resonance, this is a tool to explain how that happened. This is at the orbital level, let's say, what's happening, what is the overlap. But how can we do that using, instead of doing all the whole orbitals? So what we're going to do is we're going to draw an arrow, and this arrow is going to represent the flow of electrons. Always, the arrow starts at the source of electrons. And now we're going to make the pi bond to the other side. And so I am redrawing this down here. So I have this structure in them. I said that I will move my electrons. And if I number the carbons, this is 1, 2, 3. And now I'm going to use another arrow. And this is the convention that we use to for resonance, to resonance structures. And now I'm going to draw the resulting structure after the electron movement. So this is carbon 1, 2, and 3. And now my positive charge is here. This is all because we have the appropriate symmetry of all of the p orbitals, and we can have that overlap. But the way we represent that in resonance is, I'm going to erase this one here to have a little bit more room. Let's see. I don't want to erase my structure. All right. So we will put this in a bracket. And so now this too, a resonance structure. That's the arrow we use to represent that. And the way we draw arrow is to represent the flow of electrons. What we're saying here is that neither this structure or that represent the actual molecule. What represents the molecule is what we call a hybrid, a resonance hybrid. And what would it look like? So the resonance hybrid now, we have partial, now we see here that the charge could be either in carbon 1 or 3, and that we have some double bond character between carbons 1 and 2, and also between carbons 2 and 3. And we're going to represent that by dotted lines. So partial double bond, and now partial positive charge in the carbon 1, and partial positive in carbon 3. And this is what we call my resonance hybrid. And that is a better picture, or actually the molecule is. The charge is spread, is the electrons are delocalized, pi electrons are delocalized, and that causes electron delocalization, causes, so I'm going to write it down, electron delocalization brings stabilization. So let's do this. Stabilization. And this is what the real molecule, or similar to that. So we're making a parallel between what we saw in the orbital level now with the resonance structure. This hybrid thing is something like when we say, do you consider a mule? And the mule being born from a horse and a donkey, right? But it's not like you take a snapshot and sometimes we see a horse and sometimes you see a donkey. No, it was always a mule. So the molecule is not like sometimes it's like this, a snapshot, sometimes it's like that. No, it is always have the electrons distribute and delocalize, and this is a picture that more closely say what is a molecule like. Okay, we'll be talking more about resonance in the next videos.